Then second thing, so firstly we discuss how we can draw the uh, core of our transformer, right? Then comes the winding part. So for the winding part, your winding is wound on the core, right? So it will be somewhere look like this, right? So it will come out of the core because it is wound on the core. So for that, what we did is we have taken two boxes and then have cut it accordingly such that we will get a winding like structure, right? You understood this yesterday? Do you guys have any doubt how we have drawn this geometry? You guys understood this yesterday?
Yes, ma'am.
Yes,
Oh,
ma'am.
fine. So let's just proceed then. Then comes for the boundary. I told you that here we don't need to specify boundary. We will just create a region, and in that region we will specify in which environment we will be operating our like device, right? Of- For example, here it is transformer, right? So because I want to operate my transformer uh, in open air, so I have kept as air, means in open surrounding. We can keep water. I Yesterday I showed you, na, we have multiple options there, right? Water, distilled water, or like, so if you want to create some device for underwater, so in that environment also you can test your device. Understood? So this is the region. This is how it looks like, right? When you're making your region, so when you're drawing the region, just keep in mind that it should not touch your geometry in any which ways. Okay? So if it will touch your geometry, it will throw an error here. Fine? So your region should never touch your geometry. Then we discuss about excitation, right? So in excitation, I told you yesterday I was facing some issue, right? I told you that I'll look into it and will tell you today. Can anyone tell me what was that? What was the error that we were getting? Yesterday we were getting some error, right? While we were assigning our excitation. I told you I'll look into it and will tell you today. That's why we have not analyzed it tomorrow, right?
Yes, ma'am.
What was the error? If you will not remember the error, if you will not remember what went wrong, so if I'll tell you the correct way, how will you like understand it? Why it was like that before and why it is like that now? Even error plays an important role in learning, right? When you will get an error, you will explore it more, right? If you don't get error, you're like everything is going smoothly, then you will not learn that much. But if you get errors, then you will explore it, what is happening. You will cross check each and everything again and again, right? So error plays a very important role in learning. So you should remember what error you made. Fine? Okay. Oh, it's fine. So, I told you that for assigning excitation in 3D geometry, because you are not using wounded structure here, and you are using a solid structure as a winding here. For assigning the excitation, you need some sections, right? Yesterday I told you this part. So whenever you have a coil like structure, but you are not using the wound structure, you are using the solid way of it, like how it will look in a solid form. Then you need to add a section to assign excitation. How we added that section? The help of this, right? You remember this section we added yesterday? So these sections we added, right? For assigning the excitations, right? You guys remember or not?
Yes, ma'am.
Okay. Then uh, we assign the coil terminal to this. So while assigning coil terminal, I told you that the number of conductors, I'll keep it as 100, which signifies my number of turns, right? But it was throwing error when I assign it to winding, right? It was saying that you can only select one as your conductor, right? It was because when I have assigned add a winding here, I have selected a solid option. So what happens in solid option is you can it considers the whole part as solid. So it is like a one block. So number of conductor can only be one here in this case. So if you want to put the number of conductors, you have to select the stranded option. Understood?
Yes, ma'am.
So if you want to put your number of turns in both in 2D also in 3D also, you can put it in 2D also, but in 2D we have not used that option, right? But if you want to put your number of turns in 2D also, you have to switch it to stranded and then put your number of turns. Understood?
Yes,
So
ma'am.
it will not throw error here, but when I'll just show you the example. Okay, remove from binding. So when you will make your remove from so when you will make your coil terminal, it will look like this. You will add your two windings, primary and secondary. Then what is the next step? You assign this add terminals, right? So here in winding of primary, if I'll choose the solid option and will just assign coil terminal here, sorry, add terminal. And if I'll select this error will throw. Yesterday we were getting this error, right? It's
Yes, ma'am.
because you have to select the if you want to specify your number of turns, sorry, you have to select here stranded option. Then it will not throw error. Now you'll see primary and in secondary it's already stranded. Then secondary.
Ma'am, I have one doubt, ma'am.
Yes, yes. Please ask.
Ma'am, if we construct winding as a solid bar,
Uh,
uh, if we cannot mention tons if material is like a conductor, a solid bar. Hello,
you are saying in 2D or 3D?
3D only, ma'am. But
Uh, but if you all consider it as a bounded option, you are saying like that.
yes, ma'am.
Just
Okay.
repeating the question.
Oh,
No? Please repeat your question.
yes, ma'am. Yes. Uh, ma'am, that like those winding,
And
the
ask
winding, no, ma'am.
anything. I
There is a
know
winding, no, ma'am.
if you're
Solid bar
comfortable.
winding.
Huh?
Hello.
Yes.
We are unable to construct that hollow winding bar. Yes, right, ma'am. We are unable to construct that hollow winding.
Which kind of winding? I'm not understanding. This winding you're talking about, or like
Yes, ma'am. This is a full bar, no, ma'am.
this
By
is full bar. Yes, this is full bar. Right. Now
but
you
we are
want. Hmm.
but we
Yes.
are unable to construct only that winding hollow bar.
Only. Sorry, I'm not understanding what you are trying to say. Like,
Ma'am,
try
continue,
it in
ma'am.
different way. No, it's like I want to clear your doubt, but I'm not understanding what you are trying to say.
Ma'am, after the class, I will clarify the doubt,
Okay,
ma'am.
uh, I'll just repeat myself. If your doubt gets cleared, it's fine. If it does not get clear, then after class you can ask me. Okay.
Yes, ma'am.
So we can make our winding in this way. First is this way, right? One block way means the whole block, hollow block that you are calling it. This is one of the way, and one of the way is make it as wound structure. Maybe. Okay, I'll draw it here. So another way is we can make this also. It's not like we cannot make our coil like this, but like in 3D, this is that window. I hope you are understanding. Huh?
Yes,
So
ma'am.
if this is my transformer, I can make my coil like this also in 3D transformer. It's not like I can not make it in wound form. I can make it, but the thing is, it's not like I'll require a lot of effort to do it. I'll in the next class I'll tell you that. But this
Ma'am, I
take
think there is a tool, ma'am.
up.
I think this spiral winding, there
Ha,
is a tool.
exactly. So there is a direct tool to do this. So it's not like it will take a lot of time to make, but it will take a lot of time to simulate. Like maybe 2, 3 days, the simulation will keep on running. So that you don't want, right? You want instant results. So instead of this wound structure, I'm using a solid structure, right? Which looks like my winding only. But now I want to assign this number of turns to that solid structure. Okay. So
Yes, ma'am.
what I did is uh here I have specified that number of conductors. How many turns I want? I specified here. Okay. Now it will, I'll not say that it will be exactly same, but it will be uh, somewhat same. So it will give you near results. Okay. Approximately same results. Okay. Now
Okay,
you are
ma'am.
asking, if you are asking me if I have considered it as one conductor, what will happen? It will not give you the same result as that wound, but just for analysis part, why people considered it as one conductor only? Because see, if I'll specify your 100 conductors, it will take a lot of time to simulate. So while teaching, it is easy for me to specify it as one conductor so that I can just tell you the analysis part easily, right? So now it is like for one, like for one turn, understood?
Yes,
So,
ma'am.
so that's why many a times means I have also used like I have also used one conductor only. Fine. But now I'm telling you how to specify the number of turns also. Why I'm telling you this? Because in variable thing, I told you now we will cover variable part also. We will keep this number of turns as one of our variable. Okay. So number of turns also we can keep as one variable. Understood?
Yes, ma'am.
There might rise up like various questions like cross section will change, right? Depending on number of turns, the windings cross section, right? How much space it has occupied, right? So that we are not analyzing here. I'm telling you that very clearly. Okay. But you can explore it more. You can just imagine things more and you can do it on your own. So when you will start doing it, you will start getting multiple questions. Why it's like this? Why, if my number of turns is changing, the cross section is not changing here? Why we are not doing that? This, when you will start doing things, now you will start getting these questions. And that time you will solve it on your own. You will not even need me. Why we are doing, because it's like I'll just teach you the basics, right? But there is a lot in Ansys that you have to explore on your own. Fine.
Yes, ma'am.
So when you will start exploring, most of your doubts will get clear at that time. Now you are just listening to me. If you are not doing it also with me, then also when you will like do it yourself, you will get multiple questions, you will get multiple errors. But while solving that error, you will learn a lot. That is for sure. Okay, fine. So you guys understood this now? Like I
Yes,
tried to
ma'am.
explain it, but I am not sure you guys understood it or not. So let's proceed. Then we have mesh operations, same as we did in 2D. Okay. Then we have analysis setup, same as we did in 2D. So nothing is changing here. Now, if I run this setup, because I already tried running this, you can see here at 4 o'clock, I tried running this. So till 6 also, the simulation was not completed. When I specify my number of turns, so I'll just change this to 1 because I want to analyze this with you. I just told you, right? It will then take less time. Okay. But you guys understood now how to specify number of turns? Actually, I wanted to analyze it with number of turns only, but I think I have to keep it running for like 1 day or so. And we don't have that much of time, right? So for now, just for the analysis part, I'm changing it to one, but you can just run it with the number of turns, okay? Fine. Okay. So it's running. Here also, we will do the same analysis. Sorry, it got hang. Okay, fine. So first, what we will do is field overlay. First, winding loss. How we have calculated winding loss? Eddy current. How we have calculated winding loss? Guys, remember? We have to keep it running on. Sorry, I forgot this one. Okay. So for calculating inductance, what we did is we assigned matrix, right? So this I forgot. Again, we have to run it. So I'll just select run it. This we learn it 2D structure. You guys remember this, right? For calculating inductance, we need the we need to assign this matrix, right?
Yes, ma'am.
Yeah. Just wait a minute. I don't know why this is taking time. Yesterday it got yesterday it has not taken much time, right? When we run it. Okay, we will wait just for few minutes. If it does not get run, then we will do the same. Like I'll just repeat the analysis in 2D structure only. Just do it here. Is that fine? Because if it will take a lot of time, then we will not be able to analyze this specific simulation. I tried running it beforehand, but uh, like For 2 hours it was running and still we didn't get the result. My system got shut. Fine. So the same analysis that we did in 2D transformer, we will do here. The first thing was finding loss. So we will go to solution data. Here loss. Results are also gone. Fine. Check it. Results are there. This usually does not happen. If you just save your result, it does not happen. Yeah, I don't know something. But fine. As for the things. Because my two simulations are running, this simulation is also taking time to run. So last time when we simulated it, it has taken like 5 minutes to run, right? But now it is taking time because that 3D simulation is taking time to run. Will I tell you how to analyze the results now? Hmm. Let me search for alternate option. Hmm. Sorry, sorry, I'm actually not understanding what is happening here. The results for this are gone. 3D simulation is not running. Okay, fine. Uh, Analysis part, uh, I'll just tell you afterwards. Let the simulation get completed, then we will analyze the part. Okay. Till that time, let's proceed with the second objective. Our second objective was to do the AC analysis of the 3D geometry, right? So we will just analyze both of it uh, in 2D only, because running the 3D geometry takes some time. Okay, fine. But I'll tell you um, how to do it in a 3D geometry. So it's like in the same way what we did in 2D transformer. So what was the first step that we did for for transient analysis in 2D transformer? Hello guys?
Magnetic flux, ma'am.
No, no, no. Uh, in transient analysis, what we did, transient analysis of 2D transformer, what we did for finding core loss, what is the important thing to do? Changing the core material, right? Right?
Yes, ma'am.
Okay. So first, let's change. So I have this same geometry here. So first, we will change. This is the same geometry that we made a 3D transformer. Nothing is changed here. So first, what we will do is change your solution type to transient. Okay. Solution type to transient. Then second was okay. Second was assigning the material, right? You guys remember how we assign a new material to our core?
Yes, ma'am.
The whole class we dedicated on that, right? So do I need to repeat that, or should I just directly put the values and you'll be fine? You guys understood that, right?
Yeah, ma'am.
Yes, ma'am.
Yes. Okay, so I'll just directly put the values, and you guys already know how we got that values, because we discussed that in class, right?
Yes, ma'am.
Okay, fine. Okay, so this is, so let's first assign copper here. Then this is also copper, right? These are the windings that I'm assigning material to. For region, it is air. Type assignments है. So, copper. This box है, it is copper, not air. Region is air. Then what is left? Our core material. Edit. Add material. In relative permeability, non-linear. BH curve. Put the values of B and H that we got from the data sheet. You guys know this, no? How we have, like we got this B and H values. It is from the BH curve, right? Of what was the name of the material? 3C85, right? You can just change your material also, whatever you want. I'm just telling you for one material. You can just try it for some different material also. Even for copper, you can change your material, like you can change it to lids wire and all. But that we are not doing. At least here we are not doing. We will see in wireless transfer. Okay. Here, power ferrite 12, 1.3, 2.55, right? This also I told you. What is this? K alpha beta. This also I told you how we have calculated. We will change the name of the material as 3C85. Okay, fine. Do you guys have any doubt in this? How we have assigned the core material? I have just directly put the values because I have already explained it to you. That is the same, like in 2D transformer, I explained it to you how we can add a material. The same steps we have followed in 3D also. So you guys have any doubt in this? I hope not. Okay, fine. So if you have any doubt, please let me know. Or else, should I proceed then?
Yes, ma'am.
Like, to the excitation thing. First, I'll just hide this. An excitation, coil terminal. Secondary. I'll put it as one only. I told you about this. You can put it as per your number of turns, but just for the ease of simulation, I'm putting it as one. Okay? This is coil terminal. Primary. One swap direction. This direction also I've told you. It depends how your current is flowing. Right? Right?
Yes, ma'am.
Yeah. Then add winding. Here we will put sinusoidal current, right? 10 sine 2 into pi. This we have already this we already did in 2D geometry. So I'm not repeating myself, but if you guys have any doubt at any point, you can just stop me there and like ask me what like why I'm doing this, why it is so. Okay? Because these steps we have already done for 2D. So I don't think like there is point in explaining it to you again. So I'm just entering the values and all. But if you have any doubt, please stop me at that point and ask. Fine?
Okay, ma'am.
Yeah. Same 10 kilohertz frequency we are assuming. Add winding. Secondary. 10 sine 2 into pi into f into time. This is at winding. At winding. Assign mesh operation. Inside selection. Focus. This is also done. Then analysis. For 3 cycle, like you can run it for any cycle. So for 3 cycle, I'm selecting as 300 microsecond, 2 microsecond step size. Okay. Then for safe field, start time 0, end time 300, and this is 1. Add to list. And change it to microseconds. Then, okay. So our setup is done. So the whatever steps we have followed in 2D geometry, the same we did here. First, we change our solution type to transient. Then we change our material. So we added a new material there. So for a new material, what is the most important thing? We have to first get its data sheet. So from the data sheet, whatever data we need, that we will put here. So first is BH curve. So from the BH curve, I have taken it for 100 degrees Celsius. So the B values, you can select a set of B values and then can put a corresponding H values in the, like, can see what is the corresponding H values through the BH curve of the core material, and then form a table and put that table here, right? And then now the second thing is to calculate core loss. The most important thing that we should know is alpha beta, because according to Steinmetz equation, we wanted the values of alpha beta uh, to calculate core loss, right? Steinmetz formula I've told you, PV equals to K, F to the power alpha, B to the power beta, right? So from how we have calculated alpha and beta, that I have told you in the previous class, right? The whole class we dedicated on that only. So I don't think you have any doubt in that, right? So uh, through that method, we have calculated alpha, beta, and similarly K. So that three values we have put here, and just and now our material is ready. So our core material is ready. The next thing is assigning excitation. So we are assigning sinusoidal excitation here, right? 10 sine omega t. Frequency what we choose? 10 kilohertz. So that we have put here. So this also I told you in 2D structure, right? Then what was the next thing? Mesh operation. Mesh operation you already know by now. We are doing it for every other geometry. So I don't think I need to explain this more, right? And for transient analysis, here we have to specify the timing. So till what time you want to run your simulation, that we have to specify here. So I want it because my frequency is 10 kilohertz. So I wanted it approximately for 3 cycles. So that's why I have like uh, kept my stop time as 300 microseconds. Okay. Then time step you can keep 1, 2. So I just kept it at 2. And the most important thing, because you have to see the magnetic fields, the most important thing is you have to give the value of safe field, means at which point the your simulations should save your fields. So this you have to give. So uh, for the whole simulation, I wanted my field to get saved. So I'll start from 0, stop at 300 microsecond, or change to nanosecond. It's microsecond. is getting changed to minus. Oh, sorry. I have not replaced it. That's why. So, whenever you will change something here, please replace it in the list, or it will not show. The recent changes will not show if you will not replace it in this list. Okay. So then, I have started from 0, stop at 300 nanoseconds, and step size is 1. Okay. So one most important thing I have forgot. What is that one thing?
Boundary, ma'am.
No. Boundary I told you in 3D, it's region. Region I have given. See? Okay, I'll just give you one hint. For calculating core loss, I told you something you have to do in excitation that I have not done, or else you will not get core loss. You guys remember? You guys remember that?
No, ma'am.
So for if see for winding loss, it's fine, but for core loss, or you have to set in excitation, you have to set your core loss. Like geometry, you have to set. So it's box 1. If you will not select this, you will not get your core loss. Ansys will not know for which they have to calculate it. Okay, fine. So this is very important when you set your material. So selecting this is very important. I told you this in the previous class also in for 2D geometry. Fine. You can select eddy current effect and all also, but we are not analyzing that. So it's fine. Fine. I can run this simulation, but again, it will take a lot of time and our time will just get uh, wasted. So I don't think I'll run the simulation. I'll analyze the, I'll tell you analysis through inductor only. This results are present. Yeah. So see, after you will run this simulation, after you will run this, just click on the results, transient report, data table, loss, and then core loss score. Okay, sorry, not data table. You have you want to see the plot, right? The rectangular plot, loss. So something like this will come for transformer also. Okay, for 3D transformer also, it will come something like this only. Okay, then now I want to see average of this. So what will I do is right click on this, go to trace characteristics, favorite, and then average. So here you can see the average. Okay, fine. So this thing,
Yes.
the second thing was in field overlay. Actually, I told you I'm same analysis you have to do in 3D, but because it will take a lot of time to simulate, I'm not doing that analysis there. Okay, but same thing what I'm doing here, you have to just do it there. Okay, I'm repeating myself, but please understand that. Okay. Just select your core, then right click field B, then magnitude of B, done. It will not appear unless you will give some time. So I'll just give it something random. Okay. Okay. It will not appear if you don't give a specific timestamp there. But now I want to see it for all the timestamps. So what I'll do is I'll just animate it. Okay. Just right click, then animate. Just wait a minute. Sorry, my laptop. Sorry, my laptop got hang. Multiple simulations are running. That's why it got hang. Just wait. Okay, yeah. So like this, you will see. So on all timestamp, it will show that how your magnetic field looks when you animate it. You can export this from here. You can change the speed also. You can make it fast. You can make it slow. Fine. You can see it at particular timestamp also from here and from here also. If you change it, here the time appears. Understood? So this same you will see in 3D structures also. Same thing. Okay, fine. I'll run the simulation today. If it got run by tomorrow, then I will show you the results. Okay. So just for eddy current analysis, just analyze the winding loss. You know how to analyze the winding loss. I already told you in 2D structures, right? You guys remember that? So for analyzing individual in eddy current, for analyzing individual winding loss, just go to field overlay. So now I'm not talking about transient analysis. I'm talking about eddy current solution type. Okay, for winding loss, I'm telling you this because we have not analyzed that because our simulation is not running. So just go to field overlay, calculator, quantity, ohmic loss, whatever your geometry is. For individual coil, you can see, keep this at volume. Okay. Then integrate it and then evaluate. Because our simulation, we have not run our simulation, it is showing error. But if your simulation is properly executed, then you will not get this error. Okay, fine. So individual ohmic loss you can get, individual winding loss you can get. Then total winding loss, for total winding loss, go to result, solution data, loss. So here that loss will get displayed if your solution is executed. But for us, it's not executed. That's why it is not showing anything. So two thing is there. Then I told you about inductance matrix, right? So that also you can get it from here only in solution data type only. So all in all, the analysis of 2D and 3D transformer is same, just the way you are like drawing the geometry is different. Okay. So so there is one like assignment for you guys. Uh, what you have to do is make 2D transformer geometry and make 3D transformer geometry with with whatever with the same parameters. Like if you are using only one primary coil, so just in 3D, so just keep one primary coil in 2D, means one primary layer. And if you are using just one secondary layer, then just keep one secondary layer in 2D and analyze the like compare the result of 2D and 3D. Okay, try to do it by tomorrow if your simulation get run, or else just analyze it for your sake and see how much deviation you get in the results. Okay, fine.
Yes, ma'am.
Okay. Does anyone have any doubt in this? Like, are you understanding things, or you are just like following me? Like, don't follow the steps. Understand what we are doing. So just don't select because I'm doing it in a particular way. Just don't think that it can be done in that way only. There are multiple ways to do things here. Okay, put your imagination to work and just like what I like explore answers like anything. Okay, so when you start exploring it, you will start enjoying this application. Okay, fine. Maybe you are not appreciating it now because you are just in your third years and you don't have to make any hardware and all. So maybe you will not appreciate it now, but if you will do your MTechs or your PhDs, higher education, or if you will work in some core companies, then you will appreciate this app. Right?
Yes.
Okay, so let's just see till what we have completed. So first was introduction and 2D transformer geometry creation. So you understand. Just please, one of you, please say yes or no to me. Okay, fine.
Okay,
Uh,
ma'am.
yeah. So now you know how to draw a 2D transformer, right?
Yes,
Right.
ma'am.
So your this day one objective is completed. Fine. You know how to draw 2D transformer with variable dimensions, right?
Yes, ma'am.
You have any doubt in this?
No, ma'am.
What? Why we need variable dimensions? First, for the ease of drawing, right? Like if we want to change
Yes.
any dimensions, we don't have to again go to drawing and set everything again. And second is if we want to like change that variable and see uh, what changes we get in the results, that also we can do. Okay, so that's why variable dimensions are important. So our day two objective is also completed. Fine. You know how to
Yes,
set
ma'am.
boundary, excitation, and mesh, right?
Yes, ma'am.
Okay, so mesh, the thumb rule I follow for mesh is whatever is the dimension, I just keep it's 1/4, but it's not compulsory. Sometimes you might get error, right? Sometimes your result will not converge. So you have to just keep it somewhat less. If you'll keep it less, you might get like your simulation will take a lot of time to get executed. But if it is throwing error, then just try to change it. Okay? Just try to increase or decrease your mesh, right? Excitation, I've told you two ways. First, directly current excitation you can give, or through winding you can give, right? And then
Yes.
boundaries in 2D, you have to give balloon boundaries. You have to select the edge and give balloon boundaries, right? So our day three objective
Yes,
is
ma'am.
also completed. Then our day four objective is, you know how to calculate winding losses, individual and also total. Then you know how to get your inductance matrix, right? And also you know how to get your field plot, right?
Yes, ma'am.
So this is also done. Day four objective is also done. Okay, so I'll just make the changes accordingly. So this is not your final final manual. I'll make all the changes that I've told you in the class. For now, we are just revising this, okay? And then we did AC analysis. So transient analysis with AC excitation we did, right? There we
Yes.
learn how to add a new material. Then we learn how to animate your fields. Then we learn how to calculate the core loss, right? So this is
Yes,
also
ma'am.
done. This is for transformer. So I have told you for inductor. So I'll just change this to inductor. Okay. So don't worry about this. Then is parametric studies. Uh, this part I discussed in like for the in last 10 minutes or so in one of the class, right? You guys might not even
Yes, ma'am.
remember that.
Yes, ma'am. Yes.
Okay.
Just
So
stop the class,
I'll
ma'am. That last 10 minutes before
last
one day
10
back, ma'am.
minutes. Right, exactly. So I'll just repeat this again. Here how to, I told you how to add a core material. I told you, right? But I've not told you how to just change the number of turns and all. Instead of this, uh, I told you about current, right? Right? If you guys remember this, we have changed our current I1 and I2. Right? Okay, you guys don't remember. Okay, fine. Again, I'm again repeating this part because I told this part I just covered in the last 10 minutes in some class. So I'll just repeat this part. Then we will be done with our transformer. Okay, 2D and 3D both. So just this objective is left. Okay, then 3D transformer, how we made our geometry, you understood?
Yes.
We did just ignore this magnetostatic simulation. We did eddy current and transient. So we will just focus on that. Magnetostatic is for DC. So don't like just don't concentrate on this. Okay. I'll change this manual. So for now, don't be worried about this. Okay. So 3D transformer geometry, you know how to set excitation, you know how to set boundary, you know. Here you don't have to set the boundary. You have to give region, right?
Yes,
Right.
ma'am.
Then again, same analysis, how to get your winding losses, total losses, individual winding losses. It is in the same way, like a 2D structure. But because our simulation is not executed, I have not told you that. But I've told you how to get that. Okay, fine. So this objective is also completed. Okay,
Yeah, ma'am.
then our transient and eddy current analysis in 3D transformer. This we just now we completed this, right? We have completed this just now, right? Like
Yeah,
a
ma'am.
transient, oh, sorry, not eddy current, transient analysis with core loss, right? So
Yeah, ma'am.
what is left is just parametric studies left.
And
So that
analysis
we
part also, ma'am.
analysis part is left, but because my simulation is not executed, I will not be able to do it today. I'll just keep my simulation running the whole night. Then tomorrow we will just see the analysis if my simulation is executed. If it does not get executed, you have to do it on your own, or by the end of the course, like after 2 3 days, whenever it is executed, I'll show you. It's fine.
Okay, ma'am.
Okay. So uh, so the only thing that is left is okay, parametric study. Okay, first let me tell you the importance of parametric study. Now, I have, in terms of core material, first I'll tell you. Now I have I have to choose one material for my core, right? But I don't know for now which material is best. Okay, so I have created my geometry in Ansys because you cannot try to you want to make your transformer. You cannot try every material's core, right? So I'll make it Ansys. I'll just try their different core materials and we'll see in which material I'll get the less losses, right? That then I will use as my core material, right? But for this also, I cannot just make three geometries and assign different core materials to them and then just calculate its core loss and then compare. So what I'll do is I'll make one geometry only. In that one geometry, I'll just change my core materials and then we'll make a comparative table, or we'll plot it, or will like plot for all three of them, and we'll see which material is giving me less loss, right? So this is the importance of parametric study. So with the same geometry, you can try for different, like you can get the results, or you can get the compare rather than results, I will say comparison, because most of the time you have to do comparative studies only, right? So with on the same geometry, you can just change the current or number of turns, whatever you want, and can see how it is affecting my parameters, right? With on the same geometry. Fine. So this is the importance of parametric study. But I actually told you how to do it for core material, like how to change your core material. But I cannot show you for different core material what like comparison. Now you will ask me why. Because then you have to put the BH curve for all that core materials. So you have to like add new core materials, because the materials that are available there, you cannot get the like perfect core loss for that. You cannot get core loss for that because it does not have that K alpha beta parameters for calculating the core loss. So you have to add just like we add C385, we have to add different materials there, then we have to analyze. For two materials we can do, but I think that is a lot of work, right? So just remember this how to do it, but we are not doing it here. So what we are doing is we will not change, we know how to change it, but we are not changing this. We will just see the effect of change in number of turns and current. So with current, what will change? My winding loss will change. Okay. So we will see the variation of winding loss with different current. Okay. And with number of turns, what will change? These are actually interdependent, turns and current, right?
Current dependent.
Uh,
Yes,
right.
ma'am.
We can analyze any one of it actually. Okay, so let's just analyze current only in this. Okay, because number of turns also takes a lot of time to get running. We have just seen, right? But I'll tell you how to do this also. Your with number of turns, your inductance will get changed. So here we are just analyzing it for current. Maybe you will not appreciate the parametric study here for now, but uh, like in wireless coils simulation, You will really appreciate the parametric studies. The parametric, the importance of parametric sweep, you will understand it there. This here. Okay. But for now, I'm just telling you how to do it. Okay. So go to your geometry, any geometry. This is your day one geometry, right? So here, what we have done is uh, rather than so whatever you want to sweep, so whatever you want to change, just keep that parameter as variable. So I want to change my primary and secondary currents. So I'll keep it as variable. So I have used I1 as variable for my primary current and I2 as variable for my secondary current, right? Then now see, I want to change my current from example, my initial value of current is 10 example, but I want to see how my winding loss will vary if I change my current from 6 ampere to some 24 ampere, right? So 6 to 24, I'll take a small steps. So how, where we have to give it? We have to give it in optimetrics. So whatever you want to change or whatever you want to sweep, that parameter you have to give in optimetrics. So just right click on this, add parametric. Okay, then add. So all your variables will appear here. Okay. So example, I just want to see I1. Okay. So its initial value is 12 ampere. Now I want to change it from 6 to 18 from step with the step size of 1. I'll add it here. Then okay. In table, you can see how your current is changing. 6, 7, 8, 9, 10, 11. Like this, it will change. So for all the currents, it will calculate my winding loss and then will give you in the form of table or plot. Actually, both. It will give you in the form of both, but you can take it in whatever form you want. Then you can just click on OK. Then you will run your simulation. Now running simulation has become a problem for me. That's why I'm not running it. Then just go to result, edit current data table. Here in frequency, primary swipe, in frequency, select I1. Okay. Because you want to see with respect to change in I1, right? Then whatever loss, right? Solid loss you wanted to see, then solid loss, like winding loss, and then new report. Here a table will come. When you will run this, your table will come, which will show you with current uh, means from 6 to 18, what for the current value of 6 to 18, what is your corresponding winding loss. Similarly, you can see it from rectangular plot in form of solid loss select. In the form of plot also, you can see that variation. Okay. So this is just an example of how to do parametric study. I told you will not appreciate here, but in maybe in wireless power transfer, you will understand it more clearly. Okay, fine.
Yes, ma'am.
Okay, so I'll keep my simulation uh, on run. Okay, fine. So I'll just run my 3D geometry. If it gets executed by tomorrow, if my simulation get executed by tomorrow, I'll show you the analysis. But if it does not get executed by tomorrow or day after tomorrow, then we will analyze it in the last class. Okay, fine.
Yeah, ma'am.
So tomorrow we will start with the wireless power transfer. Anyhow, we will start with the wireless power, means coil geometry for wireless power transfer. We will start with that. But if our simulation get run, then the first half an hour we will just I'll just show you the analysis for both eddy current and transient. Okay. But if it does not get run by tomorrow, then we will analyze this in last class. Okay, fine.
Yeah, ma'am.
So that's it for today. If you guys don't have any doubt, we can end this class.